Today we want to look at writing explanations. So a lot of times I'll ask essentially, when is this happening? Or a yes or no question, but then I will write the dreaded math word explain. And so you'll have to write a sentence or two. Usually you can get away with one sentence around here. You write a sentence or two explaining why you came to the conclusion that you came to. Some thoughts about writing explanations. You want to say everything that you need to say and nothing extra. You want to say only that which is necessary and sufficient. You want to make sure you say everything that's necessary, and you want to stop when you've said everything that's sufficient. So I want you to think of necessary and sufficient. Necessary means make sure your explanation is complete. Your conclusions are based on all the things that you need. Sufficient means you didn't say anything extra. So you said what you need to say. And then stop.
Stop trying to be fancy.
That's part of it. Don't try to be fancy. Say what you need to say, and then stop. Here's the reason why. The reason that you want to stop is if you start including additional information, when you start including additional information, you risk saying something incorrect. But more importantly, you risk saying something not relevant. If you say something not relevant as part of your explanation, you're implying that that this irrelevant thing is that you think that it's actually relevant. So saying extra stuff implies that you think you need the extra stuff. That's why I recommend say what you need to say, then stop. If you're not sure, that's a cue that says, oh, maybe I don't really understand this. Let me look at this further. Instead of just trying to put out more information into your explanation, stop and think, have I said everything that I need to say? And now, if so, then I'll stop. So the reason that if we don't stop, we might imply that we think if we don't stop, then we might imply that we think something that's actually irrelevant is relevant. And then at that point, we've crossed over into being incorrect. So first thing we want to consider is we want to say what is necessary and sufficient. So those of you who think you're going to be lawyers in the future, this is good advice for that too. Say what is necessary and then stop. Otherwise, you're just going to say too much. If you're not the lawyer, if you're the client in this situation, you say nothing. So keep in mind that if you're the client, what you need to say is the empty set. You need to say nothing. So, all right, I'm not a lawyer, but I mean, that's just good legal advice. So if we don't stop, we might imply that we think some irrelevant detail is actually relevant. So that's the first thing. Your explanation needs to be necessary and sufficient. Say what you need to say, then stop. So you don't include extraneous details that aren't relevant. Number two, your conclusions must be based on things that you can observe. Your conclusion must be based on things you've observed. Your conclusion must be based on what you've observed. So your conclusion must be based on what you have observed. And quiz 2 provided an excellent opportunity for this. So a lot of us, I can't remember what the numbers were, but a lot of us identified correctly that if we're looking at the graph of the derivative, we can see that f is going to be concave down on the interval from a to b, because f prime is decreasing on the interval from a to b. We are now done. Some of you brought up the fact that f prime is negative on the interval from a to b. That is true, but that's a conclusion that we're making based on the observation that f prime is decreasing on the interval from a to b. So if we think about it this way, we observe on this problem, on the graph, we observe that f prime is decreasing. That's our observation. We conclude, because f prime is decreasing, we can conclude that f is concave down. And we can also conclude that the second derivative, f double prime, is negative on that interval. Oh, f prime is decreasing on the interval from a to b.
I have a question.
Yes.
Is it decreasing when it's under the x-axis? Is that why?
No, I'm looking at the graph and the values are going down.
Okay.
So f prime is decreasing. That's the direction of f prime. Based on this observation, we can conclude that f is concave down on the interval from a to b. And we can also conclude that f double prime is negative on the interval from a to b. But both of those things are conclusions that we're making based on observing that the derivative is decreasing on the interval from a to b. So we know that f double prime is negative, but I could not use this to justify f is concave down, because we're not looking at the graph of the second derivative. We're looking at the graph of the derivative. It doesn't matter that it's actually true that f double prime is in fact negative. That's a conclusion that we're making based on this observation. So the reason to conclude that f is concave down on the interval from a to b is that f prime is decreasing on the interval from a to b, and nothing else. So even though it's correct to conclude that f double prime is negative, if you include that in your explanation here, you're claiming that you observe that f double prime is negative when you are in fact concluding that f double prime is negative. Does that make sense? This is not necessarily even a math thing that we're working on. This is just part of the human condition. And we kind of have to fight that when we're trying to make necessary and sufficient mathematical explanations. For the most part, we come to conclusions subconsciously. So think about a memory that you have of something that happened. You're not remembering that event. You're remembering the last time you remembered it. That's why the events in your mind change over time, because you're not going back to your direct observation. You're taking all that history and all that thinking about it and all the times you've told that story, that's what you're remembering. Even if you have a very clear picture of what happened in your mind, that's not necessarily precisely what happened. That's just the way you remember it. So the human mind is a really messy thing, and it doesn't remember things. Like, it's not a videotape of what actually happened. And what's worse is that if I know enough about your memory, I can ask leading questions that make you believe something else. So that's why in a legal scenario, it's really important to not lead the witness. Once you've started leading the witness, you don't get to go back and fix that. You've already led them down the path. You've already colored their memory of the events. I'm not a legal scholar. I'm just using that as an example for how our memory will betray us, sometimes when we need it the most. Any questions? So be necessary, sufficient. Say what you need to say, then stop. Don't imply that some irrelevant detail is actually relevant. And make sure your conclusions are based on what you have observed, not what you're concluding, even though you thought this automatically.
Can I ask a question?
Yes.
Because I originally got that question wrong. What does it mean then when f prime is underneath the x-axis? Because that's what I thought was concave down instead of the whole line.
If f double prime is below the x-axis, then we're just saying f double prime is negative, and that means the function is decreasing. And that's all we would get out of that. So if I give this, I'm going to name this part C, because I can't remember when that happened. I think it was 2, 3, and 4. But on this graph, we can observe, it wasn't relevant to our interests in this particular problem, but we now can observe that f prime, so if f prime is below the x-axis on the interval from C to infinity, so f prime negative, we would also say f prime is below the x-axis. Sorry, graph of f prime is below the x-axis. Or we could just say f prime is negative. Then we can conclude the sign of the derivative, positive or negative, tells us about the direction of the function. So if f prime is negative on the interval from C to infinity, then f is decreasing on the interval from C to infinity. So when the derivative is below the x-axis, we get to say that the function is decreasing. We didn't have to say that in this problem because the question was about concavity, and our way to concavity was the direction of the derivative.
So because the direction of the derivative was going down, it's concave down?
I don't know what you mean by it. That's one of the other things we need to highlight. You don't get to use the word it anymore.
Okay,
Not you personally. No one in this class except for me gets to use the word it.
So
Because it's decreasing, so it's concave down. Those two its refer to different things.
Okay, so the first derivative on the graph is going down, meaning that it's concave down.
What's it?
The function on the graph.
The function on the graph is the first derivative. This is the graph of the first derivative. The first derivative is decreasing on the interval from A to B. That's the same thing as saying the graph that we're looking at, which is the derivative, is going down from left to right. And we say that by saying f prime is decreasing. Since f prime is decreasing, the function f is concave down.
Okay, thank you.
Any other questions? Cool. So when you're writing explanations, especially when you're new, you're going to make a lot of mistakes. You're going to include things that are not relevant as relevant details. And I'm going to make you write the whole thing over again until you've written something what is necessary and sufficient. I'm not doing this to be mean. I'm doing this because that's how we learn things. It's important that we make mistakes. If you got all the points on this quiz the first time through, I'm sorry, you don't get to learn anything new. To the rest of you that made a mistake and had to go back and fix it, some of you multiple times, good job. That's what we want to see. Improvement. Any questions? Comment? Snide remarks? Also, don't forget, I've accepted my role as the villain. So you can go ahead and if it makes you mad, then I might call, hey, you didn't round to the nearest tenth. Why'd you put so many decimal places? And then I make you copy and paste all your answers just so you can round properly. That's just math villain stuff, man. All right, so keep in mind, I won't be taken down incredible style. I do not wear a cape. All right.
Everything I needed to know, I learned from The Incredibles.
No capes. No one believes that because I've been playing D&D for like 40 years now. A little less than 40 years because I started in the very early 80s. And one of the things that bugs me about, although more people understand this now, one of the things that bothers me is that in the 40 years that I played D&D, I've never dressed up to play a game of D&D, besides like the normal putting on pants because I'm going to be in a group of other people, putting on pants and a shirt and shoes and stuff like that. I never put on some fancy hat. I'm not throwing shade at people for wearing fancy hats. If you like to wear fancy hats during D&D, I actually think that's awesome. But I don't know anybody that's specifically dressed up for that. And yet that's like this perception that we're like getting dressed up to roll some dice around a table. I'm looking at you, Big Bang Theory. That's a terrible, terrible representation of, nerdy culture. That's all I'm saying. All right. What were we talking about? Oh, yeah. So if you would recall, our new business is finding antiderivatives. That's our new game, finding antiderivatives. We're coming at this a little bit out of place. We just started talking about the fundamental theorem of calculus, so that could be running in the background. Can't decide if that's what's running in the background. But we also have to get started on finding antiderivatives analytically. Given a function, find the antiderivative of a function. So given a function, find the antiderivative of a function. And all we have to do is we're going to flip around all of the derivative rules we know. So we need to reverse all of our derivative rules. We need to invert all of our derivative rules. So we need to invert all of our derivative rules. All right. I think yesterday we just did the 1. So we know that if we take the derivative of x to the n, then we take the exponent and write it in front. We multiply by the exponent, then we subtract 1 from the exponent. That's our power rule for derivatives. And so this leads us to the integral rule. If we write the indefinite integral of x to the n dx, then we just invert this process. So multiply by the exponent, then subtract 1 from the exponent. If we invert that process, we do the inverse operation in the reverse order. So first, we'd have to add 1 to the exponents. Then we have to divide by the new exponents. Add 1 to the exponents, then divide by the new exponents. I think I wrote it in green yesterday. Add 1 to the exponents, and then divide by the new exponents. Just thinking operationally. And this is the inverse of the process that we do for taking the derivative, where we multiply by the exponent and then subtract 1 from exponent. We do the inverse operations in reverse order. All right, there is a piece that we left off. We did refer to this without the a to b on the integral. We referred to this as an indefinite integral, which is just instructions for find the antiderivative. Just like writing d over dx in front of a function says, take the derivative of that function. Writing integral function dx is notation for find the indefinite integral. So we're going to call this an indefinite integral. And we will use that interchangeably with the word antiderivative. So find the indefinite integral. It's another word for finding an antiderivative. One thing that we know is that if we take a derivative of any constant, we get 0. So if we integrate nothing, we could end up with some constant, but we won't know which one. So the way this shows up, we never write this, but this is how we're thinking about it. If you integrate nothing, something shows up. Because the derivative of a constant is 0, we lose a piece of information. That's the way I think about it. We lose a piece of information in the derivative process. So when we do an antiderivative, when we try to go backwards, there's a piece of the process that's gone, and we need more information to get that piece back. So since the derivative of a constant is 0, when we find an indefinite integral, if we want to write down all of the indefinite integrals, we have to tack on a plus c. So because the derivative of a constant is 0, because the derivative of a constant is 0, that means we've lost information in the derivative process. This is one way to think about it. And so when we do indefinite integrals, when we do antiderivatives, we tack on a plus c. That's the constant that we lost information on. We need additional information out to find out what that is. And that's called the constant of integration. So this plus c is called the constant of integration. So functionally, this just means when you find an indefinite integral, when you find an antiderivative, write plus c at the end of it. The reason for that is that there could be some constant term that the derivative doesn't understand, that the derivative doesn't know about, because the derivative of all the constants is equal to 0. This is why finding an antiderivative is not actually the inverse. It's so close, we might as well just say, hey, it's the inverse process, but it's not actually the inverse. So add 1 to the exponents, divide by the new exponents. If we think back to derivatives, we got a lot of mileage out of this. So we get a lot of mileage out of just writing powers of x. So remember, if we took the derivative of the square root of x, how did we read the square root of x so we could take its derivative?
X to the half.
X to the 1/2 power. So we're reading the derivative of x as the derivative of x to the 1/2 power. So the derivative will be, we put the exponent in front and subtract 1 from the exponent. So we read radicals as fraction exponents. When we're taking the derivative, we learn to read radicals as fractional exponents. So when we're finding antiderivatives, we should read radicals as fraction exponents. So if I want the integral of the square root of x dx, we'll do the same thing that we did before. We will read the radical as a fraction exponent. And then we'll just do our indefinite integral process where we add 1 to the exponents and divide by the new exponent. So we add 1 to the exponents and then divide by the new exponents, which will flip the fraction over. And because we're doing an indefinite integral, we'll put a plus c at the end of it. If you forget the plus c, I take off 1,000,000 points and it takes you all the way back into algebra. I'm just kidding. 1,000,000 points is more like pre-algebra. I'm just kidding. That's not how it works. You don't lose a level. So more terminology, because we mathematicians, we love our terminology. When we write the antiderivative with a plus c, we refer to this as the general antiderivative. The antiderivative with the plus c is called the general, oops, not the general antiderivative. So if I say find the general antiderivative, now you really need that plus c. On a related note, this plus c business is also the reason that in the fundamental theorem of calculus, we said things like capital F of x is an antiderivative of little f. Questions? Let's think back to calculus again. I set the Wayback Machine to oscillate, so we're going to go back and forward. I hope you all took your seasick pills today. Oops, I'm trying to write equals. How do we read 1 over x to the third when we wanted to take its derivative? What did we do there?
Is it x to the negative 3?
Right, we just read the x to the third in the denominator as x to the negative 3. So we read this as x to the negative 3. Then we just follow our rules. We add 1 to the exponent. Sorry, we multiply by the exponent. We're doing a derivative. And then we subtract 1 from the exponents. So we can write things with negative exponents. We want to be able to use negative exponents when we're taking derivatives. This is just me advocating for the use of negative exponents more often. Just like we can get rid of radicals, I think, at this stage in human evolution and just replace them with fractional exponents. I really think we can just kind of like get rid of this square root symbol. I don't actually think we can get rid of the square root symbol. It'd be like trying to switch signs that we drive on. It just wouldn't work. It'd be too much of a disaster at this point. Like trading pi for tau it's a great idea, but nah, totally impractical. Since that's a thing, this negative exponent business is something that we're going to do with derivatives. It's also going to be a thing that we do with antiderivatives. We're going to read x to the third in the denominator as x to the negative 3 dx. The dx at the end is part of the notation, integral dx. So once we've written as things as a power of x, we add 1 to the exponents. Negative 3 plus 1 is negative 2, and we divide by the new exponent, negative 1/2. Then we don't want to lose a million points, so we'd be like plus c. Don't just make the plus c a habit, otherwise I could ask you a derivative and you'll stick a plus c on the end of it. Because you're just like, well, I'm on autopilot. It's like when you're driving somewhere on the weekend and the first part of your journey is the same as when you're driving to work, so you end up just driving to work because you're just like on autopilot. So just like with derivatives, we want to write powers of x when we can. Just like with derivatives, we write powers of x when we can. Just like with derivatives, write powers of x when you can. So don't do this when you want to do something else, because this is math and you don't do one thing all the time. But a great strategy is to write powers of x whenever possible. Any questions?
Why isn't it just negative 2? Why isn't negative 1/2?
We divide by the new exponent. So we
Is
add
it-
1 to the exponent and then divide by a negative 2. So 1 divided by negative 2, that's the negative 1/2. So we add 1 to the exponents, then divide by that new exponent. Negative 3 plus 1 is negative 2, so we divide by negative 2. Any other questions? If we think about this process, we add 1 to the exponents, then divide by the new exponents. At some point, this is not going to work. So I can't always do this. I can't always do x to the n plus 1 over n plus 1. When would I not be able to do this? What's wrong with this statement? Can I do this process for all the different values of n? Can I add 1 to the exponent and then divide by the new exponent for any value of n that we want? We can't divide by 0. So if this n plus 1 ends up being 0, then this is no good. So I can't use this formula when n is equal to -1. So I'm going to add 1 to the exponent and divide by the new exponent, so long as n is not -1. I don't get to use this if n is -1, because then I divide by 0. The math cops come and arrest us, and it's like a whole thing. You don't want to mess with the math cops. Nobody remember that show, Math Cops? Math Cops, Math Cops. What you gonna do? What you gonna do when you divide by 2? It didn't last very long. But it was still a better depiction of geek culture than Big Bang Theory. All right, what are we talking about? Oh, yes. That's okay, because we have an answer for when n is -1. What's the derivative? Well, the derivative of what function, we'll think of it backwards, is 1 over x. This is a famous one. What's the derivative? What derivative of what function is 1 over x? Because that'll tell us the integral of 1 over x dx. Natural log, not just natural log of x. So the derivative of natural log of x is 1 over x. So we can't use our add 1 to the exponent, divide by the new exponent when we have 1 over x, but that's okay. We have an answer for that. The integral of 1 over x is natural log of absolute value of x. Oh man, why do you got to mess with us, man? Leech, what are you doing to us? So natural log has a restricted domain. So the domain of natural log x has to be positive. X can't be 0, x can't be negative. But 1 over x does not have that restriction. 1 over x is like, oh, as long as it ain't 0. In this direction, when we take the derivative of natural log of x, it didn't really matter, because natural log of x is like, oh, nope, x is always positive. And 1 over x is like, oh, don't care. That's fine. Then I'll always be positive. But over here, 1 over x is like, oh, nah, negatives are okay. And so that's why we need the absolute value. If you forget the absolute values on your natural logs when you're doing antiderivatives of 1 over x, that's minus 1,000,000 points. I'm just kidding. Even to take off points, I have to be in a very bad mood. And after I do that, I'll feel bad. I'm like, oh, it's not even that you even saw that I gave you 3 out of 4. I'm like, oh, no. I'll just put it back. And then I'll type a reminder. It's like, oh, hey, don't forget absolute values. So the reason that the absolute values are there is so we can match the domain of 1 over x. That's really hand wavy of an explanation on my part. And I'm just going to leave that hand wavy explanation there. So absolute value to match the domain of 1 over x. So going in the derivative direction, it was fine. Natural log of x said, hey, x has to strictly be greater than 0. And 1 over x said, okay. But in this direction, in the integral direction, 1 over x is like, oh, so long as x isn't 0. And then natural log is like, but negatives. So we absolute value the natural log of x. Any questions? Great. That's going to get us started on finding antiderivatives. We've got to look at all the rest of the derivatives that we know and turn those around into antiderivatives. And then we have to take the rules for derivatives, product rule, chain rule, and figure out how to invert those. So that's our big plan. Invert all the derivatives. And this includes product rule and chain rule. You might be wondering what happened to the quotient rule. I've got the product rule and the chain rule. We don't need the quotient rule. The quotient rule is just the product rule and the chain rule together. So we don't technically need it. It's handy to have sometimes, like in Calc 1. But when we go to invert things, we're like, well, now let's simplify our lives. Let's just start invert the product rule and the chain rule. Any questions? Comment? Snide remarks? All right, just to clarify, as far as being the villain goes, I'm only the villain when I need to be the villain. If you're like, oh man, Leech, I accept that. I'm not actively trying to, like, destroy your village and stuff like that. Any questions?
Yeah, what was f of 3?
F of 3 was, no, I can't remember. You're just going to start off at f of 0 and calculate the integral from 0 to 3 by calculating the area under the curve from 0 to 3. That's where it stops being positive, because that's when the derivative goes from positive to negative. And so the function goes from increasing to decreasing. That's where our maximum is. So just find the area under the curve between 0 and 3. I think it was like the area under there was 5. So the maximum value should be 3. All right. Any other questions? All right, that's it for today. We ran a little bit over time. Sorry about that. Make sure your explanations are necessary, have all necessary and sufficient information. Say what you need to say and then stop. Just play lawyer. Pretend that you're being a lawyer and you're only going to say what you are legally bound to say, and then you will stop. Don't offer up anything else. Also, make sure your conclusions are based on things that you can observe and not conclusions that you've already made. All right, that's going to do it for today. That's going to do it for this week. I will see y'all on Monday, and thanks for playing.